Hello and welcome back to Let's Code Physics. We are in episode 6, the final episode in our subscriber tribute. This is a thank you to our 600 plus subscribers in 60 some odd countries. Each one of your countries is represented here in this box of bouncy balls by a single bouncy ball. The mass and size of each of these bouncy balls is proportional to the number of subscribers that we have in that country. And we've also recently added in a calculation of the temperature and the average pressure of this box of bouncy balls. What we want to change now is we want to take this model, which has been working pretty well for us, but this model is limited in that it's two-dimensional, right? That's all happening inside this plane, so the box is really a square. What I'd like to do this time in our last episode in this series is turn this into a legitimate box, a three-dimensional box. So what we're going to do is we're going to take the code that we've got so far, including the temperature and pressure calculations, and we're going to extend this thing out to 3 dimensions. What that means that I need to do is I need now, instead of just a left wall and I have been calling this thing right wall this entire time. Y'all have probably been yelling at me about that the entire time. I mean, we never actually reference them, so it's not really a problem, but still. There we go. That has finally gotten fixed. I just saw that. Oops, I don't want to copy everything. I just want to copy these two. There we go. So I need to add 2 more walls. I need to add a front wall, and I need to add a back wall. So we have a wall on the left, a wall on the right, a wall on the top, a wall on the bottom. And so now this front wall needs to be located now in the Z direction. So I'm going to take this box length, and I'm going to move that from the Y coordinate to the Z coordinate. And so its size needs to, well, let's talk about the size in just a minute. Let's see. Well, I guess I need to start thinking about the size now. So every single one of these now needs to have a size of 2 times the box length. So that way it'll end up being it'll end up being box length in each direction. So actually what I want to do now is I want to change the other sizes into this. Actually, the easiest way to do is just copy the whole thing. So I need to expand all of these walls to be the entire size of the box. There we go. And then I can do the same thing here for the back wall. It's going to be located at, it's going to be located at 0, 0, negative box length. It'll be located at the back. And then here I just need to again take the size, copy, paste. There we go. Cool. So that sets up the 3-dimensional box. Now, part of the problem now is going to be that I've now got a wall in front of the simulation. I want to be able to see it. So let's give this thing that I found a new argument you can use called the opacity. Let's make this thing's opacity 0.1 so that it'll be mostly see-through. In fact, why don't we go ahead and add that onto every single one of these just so that we can rotate the box and see from every side. So I'll put that in after every color. Oops. Copy and paste, paste. So I have an opacity. Okay, cool. So if I just do that, then I've added in, that I've gone from the square to the 3D box, but the bouncy balls themselves are still being initialized in the XY plane. So what I need to do is I need to now give them a randomized Z coordinate. So let's take our code here. We're going to copy and paste. The beautiful thing about, expanding something's dimensions is that when you're using Cartesian coordinates, a 3-dimensional problem can usually be broken down into 3 one-dimensional problems. That's why we study one-dimensional problems, is because a 3-dimensional problem or a 10-dimensional problem or however many dimensions you want to go to is almost always broken down into that many one-dimensional problems. And then, of course, I need to do the same thing down here for the velocity. Let's get on this way. There we go. And we'll call this thing Z random. Oops, not capital. Not that it matters. Oh, and I never gave this thing a Z component. Well, good thing it took it as 0. I'm just discovering all kinds of oversights here. Okay. So we've set this up where the bouncy ball is less than or equal to the number of bouncy balls. Beautiful. So we're looping over that. I don't know why I just read that part. This has been a fun series, but I offer it to you as my subscribers. But I will be glad when I'm not stuck in this box anymore. Rand Althor does not like to be put into a box. So let's see. So now we're randomizing that in the Z direction. Now the beautiful thing is there's not really anything else that I need to change. Oh, there is one other thing. Gosh, as soon as you say that, Brian, you know not to say that by now. Okay, so what I also need to change is the bouncing off of the front and back wall. So we're going to change these Y's into Z's. Y into Z, Y into Z, Y into Z. You need to change Y into Z, Y into Z, Y into Z, and one more Y into Z. I think that's the last of the Y's that I have there. Yeah, I don't see any Y's in there. I see only Z's. I don't know about other Y's. Okay. So I've checked that. I don't think there's anything else that I need to change. I know I said that like 10 seconds ago, and it turned out not to be the case. But basically, the calculation of this R vector is just given in terms of the position vectors. It doesn't care whether these are in the X, Y, or Z directions, or whatever combination thereof. And all this parallel perpendicular component business still remains the same. Only the parallel direction, the center to center direction, is going to change. Now the plane perpendicular to that is not going to change, so that's nice. I can still calculate the kinetic energy. I can still update the velocities this way, and I can still update the total pressure this way. Cool. So I should now, if I run this, I should get a 3-dimensional box of bouncy balls. And then my tribute to you, our subscribers, will be complete. And I do have one more thing I want to try after that, but this will sort of be the final product, is this 3-dimensional box of bouncy balls. Whoa, goodness! What have I created? Oh, well, this looks, I've been playing a lot of Minecraft, and this just looks amazing. I don't want these things' thickness to be box length. Oops. So let's go back up to here. Right. Okay, so let's think about this. So the left wall in the X direction needs to only be a little bit thick. That thing looked cool. You know what? I'm going to save this as a copy because that was just really cool. Wrong, but really cool. There we go. And this is still the original. Okay, yeah. So let's put this back to 0.1 and this one back to 0.1. And now for the top and bottom, I want to change the Y thickness. 0.1. Seriously, for a second there, I thought that I had forgotten to turn off Minecraft from earlier and had discovered some amazing new ore or something. All right, let's try that again. Okay, there, that is more of what I expected. So here we've got our 3-dimensional box. I can rotate it in any direction. I can clearly see where the walls are. I can even see a thickness to it there, so that's cool. And so I can see these things bouncing around. I can see them bouncing off the walls. They are not moving around too terribly much, so let's give these folks a little bit larger of a maximum momentum, because now that it's in 3 dimensions, you don't notice it as much. Let's bump this up to 50 just to see this thing. Okay, so they're colliding a little bit better now. Here's a cool head-on view. Okay, so now instead of Minecraft, I've got the Tesseract. Isn't that wonderful? I just had to do it myself, Okay, cool. So we've got these things bouncing around. Now, of course, the thing about 3D is that they're not necessarily going to collide off of each other as much, right? Because before, if they're headed this way, they're definitely going to collide because it's 2-dimensional. But now that's 3-dimensional, they could look like they're headed this way, but really be doing this number, right? So we might not have quite as many collisions between the particles as we had before. In fact, I'm guessing that we don't because our kinetic energy is staying so much more consistent. So here's another neat thing that we can do to visualize the difference that this has made. I don't see the need to print the temperature anymore. Sorry, one little aside here. Let's hash that out. There we go. one change that I could I could pick one bouncy ball and then watch its trail. I could turn on a trail for it. I only want to use one for that one. I don't want to have a bunch of trails running around. So we're going to pick a random country. So we're going to go from 1 to 68 on random.org. The result was 68. Well, I have to accept the random result. So that would be the very last one. The very last country on the list is Hong Kong. Hong Kong, you are going to receive a trail on your bouncy ball. Congratulations. So what we're going to do is, before I start the loop here, after I've created it, before I start the loop, I want to say that bb underscore list of 68 dot make underscore trail equals true. There we go. So now I've turned on the make trail for Hong Kong. So now we'll get to see where Hong Kong goes. Sphere has no... what? I may need to look into this. Okay, let's try the thing I didn't want to do. Make trail equals true. Yeah, that's the thing that I didn't want to do. Okay, so I'm not sure why this didn't work. Based on my understanding of how the little dot notation works, that should have been able to work. I've even tried changing the number there. So what I'm going to do is I'm just going to explicitly put in the make trail, and we're going to have that be equals a Boolean here of IBB equals 68. We're just going to manually put that in. So this thing will be false for everybody except for Hong Kong. Not 6,800. I don't have 6,800 countries. Pretty sure there's not 6,800 countries in the world. Pretty sure. Don't quote me on that, but I'm pretty sure. Okay, cool. So that worked. Okay, so there is Hong Kong zipping along. So it is traveling at one of the faster velocities since it has one of the lower masses. We can see it bouncing off the walls. So it did have a collision with one of the particles here. It had a collision with another bouncy ball here. It passed just under the US there. Okay, we had another collision right there. So you can see it's kind of going in the spiral in general until it bounces off of another bouncy ball. So this is kind of fun to watch. Actually, let's forget these for a little bit. Ooh, that's leveling off quickly. That's kind of nice. Whoa, big tesseract. Okay, there we go. So this is pretty cool to watch. So this is the trajectory of just one of these bouncy balls of Hong Kong, of one of the lightest ones. So you can see it encounters a few collisions along the way, but mostly it's colliding with the walls. Cool, so that is pretty awesome. Okay, so what I'd like to do now is I'm going to save this thing. What I'd like to do now is I'd like to... I need to stop beginning sentences like that. I would now like to modify the experiment that we did last time, where last time we were able to vary the temperature and the pressure by varying the by varying the maximum momentum. I'd now like to do a similar experiment, but this time vary the volume. So this will be kind of fun because now that the thing is 3D, I can explicitly vary the volume by changing the box length. So what I'd like to do is instead of looping over the max momentum, and actually let's hash that out in case we want to change that back in a little bit. I now like to vary the box length equal to, we've originally got it as this thing, which seemed to work out pretty well. What do you say we cut that down by a little bit there, and then let's hash that out. So we'll say while box length is less than or equal to, let's see, that was at 500 last time. Let's go all the way up to 500. Let's go all the way up to 1,000. Why not? Cube root of 1,000. There we go. And so what I need to do is I need to get rid of this part with the box length because we've already set it by incrementing over the box length. And now I need to uncomment this maximum momentum here so that I always keep the same maximum momentum. Now let's see, I am randomizing their positions based on the box length, but I'm not randomizing their momenta based on the box length, so that is good. Am I randomizing their sizes based on the box length? No, I'm randomizing their sizes based on their masses. Yeah, just the masses right there. Cool. Okay, so what I can do now is I can come down here. All right, everything's written in terms of box length, so that's good. So that will update. And now instead of updating the max momentum, I want to update the box length equals box length plus some amount. And I need to find out what those numbers actually are that I'm using. So I've got 500 to the 1/3 power gives me 8. And 1,000 to the 1/3 power, that gives me 10, right? Pretty sure that still gives me 10. Yes, so I'm going between 8 and 10. Not a huge difference. Guys, that's not a huge difference. Okay, let's increase that to maybe 2,000. Tell you what, let's just make it from 8 to 13. Let's forget this cube rooting business. Let's go from 8 to 13, 8, 9, 10, 11, 12. 13, yeah. I'm so indecisive. Let's go from 8 to 16, because then we're doubling it. We'll go from 8 to 16 in units of a half. That'll give me 16 data points. That's not a lot of data points, Brian. Let's go in units of 0.1. There we go. So we are increasing our box length in units of 0.1. Yes, that's good. I need to change the nature of the thing I'm graphing. First, let's make this a clean change from 8 to 16. Now, of course, that is going to change the volume by a greater percentage, because volume goes like the length cube, or rather the volume is the length cube. So this is now going to be temperature versus volume. But I'm also potentially going to change the pressure. Oh, so this is where things get interesting, because I used to have the volume fixed. There's no way for me to keep the temperature fixed or the pressure fixed. Now that I'm changing the volume, Oh, okay. Let's do this. Let's do pressure times temperature versus volume, because that's what's on the, no, excuse me. Temperature versus pressure times volume. There we go. Because that's what's on the right-hand side of the ideal gas law is pressure times volume, right? Excuse me, the left-hand side. On one of the sides is PV. On the other side is constants times temperature. Okay, so we're going to have pressure times volume instead. Okay. So let's come down here and let's see. I want temperature. Sorry, what did I say I was going to graph? Temperature versus pressure times volume. So I want temperature. Oh, so I didn't want to change that. Average pressure times box length cubed. Okay, so this is now, I'm incrementing the box length. I've got the same thing going on with the animation scene being deleted. I've got the same graph being created for my experimental results, which is going to be the temperature versus the pressure times the volume. I'm incrementing the box length. I'm not doing anything to maximum momentum, which should keep temperature more or less consistent, because that determines the, well, no, that doesn't determine the max kinetic energy, because it's max momentum, not kinetic energy, and kinetic energy goes like p squared over 2m. So this should be interesting. We'll get temperature versus the pressure times the volume. And yeah, so I'm going to set this thing running, and I'll cut out. I'm guessing it'll take another 20 minutes or so, just like in the last video. And so I will get this thing started, and then we will cut away and fix an error. Oh, yeah, I just need a colon there. There we go. Hopefully that's the only mistake. Okay, so I'm just going to cut away for now. Oh, shoot. You know what? I never made this thing 3D. The whole reason that I came here today. So let's see. Yeah. So that, okay, yeah, that's why I kept both these windows open, so that I could change the thing to 3D. Oh, goodness. Okay, so I need a front wall and a back wall. That's the first thing that I need. The beautiful thing is that all I have to do is copy from the code that I developed earlier and paste it into here. Paste. Tab. Everything else is fine. Yeah, everything else is fine. Good. So I've got a front wall and a back wall now. So that's pretty cool. What else did I have to change? Yes, I have to put in the Z random. Copy. Come over here. Paste. There we go. All right, and then we're going to add in the comma ZR here. This is why I left the animation in, was so that I could tell whether I was getting the computer to do what I actually wanted to do. You know, there's a oh, that was actually supposed to go down here. My bad. There's a saying in programming. The computer is a wonderful thing because the computer will do exactly what you tell it to do, and that's what makes it wonderful. The computer is also a frustrating thing because the computer will do only what you tell it to do. So if you don't tell it to make the box 3D, it's going to keep the box two-dimensional, just the way it is. All right, so I've got the positions made into 3D now. Extruded, I think that's the term I'm looking for, is extruded. I tell you what, let's... Yeah. Rate of 10,000 will be fine. Yeah, that's fine. That's all fine. But I do need to add in checks for the Z wall for the front and back walls. So I love this tabbing business, is you can visually check to make sure everything looks appropriate. Okay, cool. Nothing else had to change for 3D, I don't think. Okay, cool. All right, let's try that again. F5. Oh, whoa, what happened there? Oh, I didn't change my dimensions of the other thing. Not that that really matters for the purpose of the calculation. I didn't get my tesseract. I want my tesseract, dang it. Let's see, position there, size, 2 times box length. Right, so these things now need to be 2 times box length. Copy and paste. This is why animations are so important, really, is that you've got to be able to visualize what it is that you're doing in the computer, because otherwise, you know, it'll look fine and you'll get results and you'll publish those results, but it might be for, you know, completely the wrong coordinate system or something. There we go. Oh, I didn't turn off the other folks' opacities. Oh, well, it's just going to keep resetting anyway. So now I can't see through that part. See, that's the difference that opacity thing makes, that it makes it semi-transparent. Okay, cool. So this is running appropriately now. So as long as I get, you know, some nice dots in here, I should be able to cut away now and return when we're ready to discuss the result. So see you in a few minutes from my perspective. See you real soon, your perspective. I'll see you after the break. Okay, so we have let this code run for a few minutes now, and I guess I was mistaken in how the average temperature would behave, because the average temperature has been roughly constant, which I suppose does make sense because the thing is that all the momenta are between 0 and 10, and that does actually fix the average kinetic energy, more or less, being between 0 and 10 squared over 2m, but the m is different for each one, so who knows. Okay, so what I'm doing now is I'm graphing the pressure versus the volume. Now, those should be interesting because those are both on the same side of the ideal gas law equation being multiplied together. So this should give us an inverse relationship. So let's actually see what that does. Okay, so again, I will let this thing collect some data and then be back in just a second. Okay, so the code ran successfully, and we've now got the pressure versus the volume. So with a constant temperature, which we are generating thanks to the uniform distribution of the random number generator, we are getting a nice inverse curve here, since it's PV equals some constants times T, P times V is a constant, and so that means that they should be inversely related. And that's roughly what we're getting here. So this thing works out pretty well as an ideal gas simulator. Some other things to try might be to make the bouncy balls of equal size and mass, since then the ideal gas law works out a little bit better. So this has been my tribute to you, the subscribers, with the bouncy ball animation. Hope you've enjoyed it. And also hope you have a wonderful Thanksgiving. We will be taking the rest of the week off, and then we'll be back next week for one more series, and then we'll wrap up season 1 with a holiday special. So thanks so much for watching. See you next time. Bye-bye.